Okay, atomic theory review. First and foremost, history of the atom. You need to know each of these guys, each of these dead guys, and their accomplishments and what they contributed. You do not need to know dates or too many details. Dalton, atom is a hard, indivisible sphere. Okay? Then, J.J. Thomson came along with his plum pudding model. Thomson. He discovered the electron. He deflected a cathode ray tube in a electric field and said that their part of the atom is negative. Most of the atom is positive, but the negatives are embedded in the atom like raisins in bread. Okay? Then came along Rutherford. He is important. Rutherford said that there is a positive, dense, positively charged nucleus. The electrons are around the outside, but most of the atom is empty space. He came up with this in his gold foil experiment, empty space and dense positive core. Okay, Thomson will give him the electron and indivisible sphere. Okay. Rutherford did this gold foil experiment. The gold foil experiment was where he shot alpha particles, which are helium nuclei, so they're positively charged, at a piece of gold foil. Most went straight through, a couple were deflected, so he determined that the atom is mostly empty space, but with a dense positive nucleus. Okay? Who came next? Bohr. Bohr is probably what you picture when you think of an atom. A positive nucleus and electrons in orbits around them. Okay? Sometimes this is called the planetary model. Not orbitals, but orbits. Okay? Finally, the current model is the electron cloud model or the wave mechanical model. Electron cloud. That is where those SPDF stuff that I teach you comes from. You've got a positive nucleus, and then the electrons are kind of in waves around the outside. In orbitals, which is based on probability, where you're likely to find an electron, okay? Where you're most likely to find an electron. They're moving far too fast for us to know precisely where they are, right? Subatomic particles, you need to know protons, neutrons, and electrons. Let's start with protons. They have a mass of 1, and their charge is positive, and they're in the nucleus. Neutrons. They have a mass of 1. They have no charge. And they are in the nucleus. Finally, electrons. They have no mass, so a mass of 0. Okay, it's just so much smaller that we can assume it's 0. They have a negative charge, and they are outside the nucleus in orbitals, buzzing around. Okay? Protons, neutrons, and electrons. Anything that says in terms of subatomic particles, you need to tell me about protons and or neutrons and or electrons. Okay? Those are subatomic particles that you need to discuss. Now, what you should be able to do is if I give you an isotope is an atom that has a different number of neutrons than other versions of that element. Okay? So let's say nitrogen. Here's nitrogen 15. You should be able to tell me the atomic number, the mass number, the number of protons, number of electrons, number of neutrons, nuclear charge, and I think that's it. Okay? First and foremost, from this, the fact that it's an N means it's going to have the same atomic number every time, okay? The fact that it's an N identifies the element. The number 7 down here, I got that from my periodic table. This is my atomic number. that identifies the element, okay? If I add a proton, it's going to affect my atomic number, and it's going to affect my mass number, which we'll talk about, but it's not going to be nitrogen anymore. If I add a proton, it's going to have 8 protons, and it will literally become oxygen. So this defines an element. This determines what the element is. So atomic number is 7. Atomic number is the same as the number of protons. There are 7 protons. It's also the same as the nuclear charge. Why? Because the nucleus only has one type of charged particle. That's protons. So the number of protons is the same as the charge on the nucleus. Okay? You do not use oxidation states for nuclear charge. All right. Additionally, if this were an ion, I would give you a charge up here, and I would say nitrogen plus 1, for example. Okay? If there's no charge there, it's not an ion, it's an atom. Okay? So an atom is always, by definition, neutral. When I say neutral, that means the protons, the number of protons, equals your number of electrons. So, since I do not have a charge listed here, it is a 0, it is a neutral atom, okay? And that means that my number of protons equals my number of electrons. So, I have 7 electrons as well. Finally, my mass number is what's listed up here. This is my mass number. An extremely important equation for you to know is the mass number equals the number of protons plus the number of neutrons. Why? They are the only 2 things that have mass. Electrons don't have mass, so why would they contribute to the mass number? So the mass number of this isotope is 15, okay? And the number of neutrons I can just plug into this equation and solve. I have 15. How many protons does it have? It has 7 plus my number of neutrons. Solve for number of neutrons, you should get 8. All right? That's what you need to know about subatomic particles. Last thing you need to know about subatomic particles, forgive me, is how to change electrons if it is an ion. Okay? So I'm going to erase mass number, and I'm going to give this guy a charge. I'm going to give it a charge of -3. Okay? What that means is that the nitrogen atom I'm talking about has an overall charge of -3. That does not mean that it lost 3 electrons. Okay? It does not mean that there are 7 electrons. It does not mean that there are 7 minus 3 electrons. It's the opposite way. It means it has 3 extra electrons. So if you have a negative charge on your ion, that means you add electrons. If you have a positive charge on your ion, that means you subtract electrons. It is not the number of electrons, the charge that I'm giving you, not the number of electrons subtracted or added. It is the overall charge of the atom. So in the case of nitrogen 3 minus, I don't have 7 electrons anymore, okay? I have 7 plus 3, so I have 10 electrons. So only in the case of an ion do your protons and electrons not equal each other, okay? In the case of an isotope is when your mass numbers don't equal each other. So an isotope of nitrogen would be nitrogen 14. The only thing that's different there is the number of neutrons, okay? All right, average atomic mass. We're going to do this relatively quickly. You need to know this formula. The formula is the abundance times mass plus abundance times mass, etc. Okay? That is your average atomic mass. You need to know how to calculate that, okay? It should match what's on your periodic table. That decimal on your periodic table, here's carbon in that little box that carbon lives in, -4 plus 2 plus 4, and I think it's 12.011. Okay, that's all from memory. I hope that works. This is your average atomic mass. It's the weighted average of all the naturally occurring isotopes. Naturally occurring. Not artificially produced, but naturally occurring isotopes. So, let's do chlorine, for example. Chlorine So naturally occurring isotopes are chlorine-35 and chlorine-37. Chlorine-35 is, I think, 76%, and chlorine-37 is 24%. I lied, it's the opposite. That's all right. Doesn't matter. Okay, here is your mass. That's your mass number of that isotope. These are two different isotopes of chlorine. And here's your abundance. Make sure that you turn your abundance into decimals by dividing it by 100 or moving the decimal place over 2. So when I plug into this formula, what I'm going to get is 0.76 times the mass of 35. There's my mass, okay? Plus, make sure you put it in your calculator correctly, 0.24 times the mass of 37. Your answer should be between 35 and 37, should not be outside of that, and it should be closer to the one that's more heavily weighted. So it should be closer to 35 than 37 because there's more. The percentage for the 35 isotope is greater than the percentage for the 37 one. Ground state versus excited state. Okay. Here is the nucleus of an atom. There's the positive charge. Here are your energy levels. Okay, so this is kind of like a cross section of an atom. Here's an electron. And let's say there's another electron here and another one here. Okay? This is not the whole atom, it's just kind of a cross section of an atom. So, what happens? This is the ground state. Okay? This is the ground state of an atom. Everything is in the lowest energy level that it possibly can be. So we could assume that there's probably 2 electrons in this first shell. This is n equals 1. That means the first shell. And this is n equals 2. That's the second shell. That's it. That's what that n means. What shell are you looking at? Okay? So, let's say that we have 2 and 2 electrons. We have 4 electrons total. That means if it's a neutral atom, we are looking at beryllium. Beryllium's electron configuration is 2,2. That's its ground state. That's the lowest possible energy. Okay? The lower the number of n, the lower the energy. So, if I'm going to make this atom excited, I'm going to take energy and it's going to go into the atom. The atom is going to absorb it. Absorb. What happens is these guys are going to jump up. They will jump up various amounts depending on how much energy they absorb, okay? They may even go, some of them might not even move, okay? That was unfortunate. That's all right. Some of them might not even move, all right? So this one might not have gotten enough energy to jump up a level, and it depends on how much energy was absorbed, okay? So they jump up a level. You don't lose or gain any. It's still electrically neutral because you still have equal numbers of protons and electrons. So then they are in the excited state. They don't stay there very long because it's high energy. So what happens next is then we have 3. Okay, so we've got 2 of them, we'll say, are up here, and we've got 1 of them that's here. Then when they jump back down, let's use a different color, and they jump back down to maybe, let's say, the ground state, they have to spit out the energy that came in. The energy is conserved. So the energy comes out as light. Okay, and this is where the bright line spectrum comes from. It comes from the energy coming out when they drop back down from the 3rd shell to the 2nd shell, for example. Energy is lost when you go from the higher energy levels like 3 to the lower energy levels like 2. Energy is spit out. Okay, it is lost. They are at a lower energy level when they're closer to the nucleus. This is where the bright line spectrum comes from. Remember, the bright line spectrum are like fingerprints. Those are the discrete lines that you saw when we did our atomic theory, when we did the spec lab, and it was dark in the room. Each of those colors represents a different jump. The greater the jump, going from energy level, for example, 3 to 1 versus 2 to 1. 3 to 1 is going to be a higher energy jump, and it's going to give you a different color line. Last thing you need to know is quantum electron configuration. Again, you need to know this for me, not for the Regents exam. So what do you need to know about this? I will always give you these boxes. This is an orbital diagram, and you do have to fill it out, even if you can do it without them, okay? So they'll be labeled for you. Let's say 1s, 2s, and 2p. And I will say, give me the quantum electron configuration for nitrogen. What do you have to do? Look at nitrogen on your periodic table. Find its electron configuration. It is 2-5. There are 7 electrons. The electron configuration is given to you. That means there are 2 in the first shell, and there are 5 in the second shell. Okay? Here are your second shell. They both start with a big 2. Here is your first shell. Okay? If I was talking valence electrons, your valence electrons are your outer shell, your highest energy shell. These are your valence electrons. So nitrogen has 5 valence electrons, and they're spread across the S and the P subshells. First shell, you need to have 2 electrons. So you're going to draw them. 1 up, 1 down. There are 2 electrons in your first shell. My second shell, I have 5. Okay? I can put 2 in my 2s level, and then I have 3 remaining to spread out in my 2p level. Do not draw them like that, okay? Why? You want to spread them out across a subshell if you can. So, in this case, the electrons can all have their own room, so they might as well. When you start filling them in, do 1, 2, 3, and that's all they need, and then go back and double them up. They must be spread out because an atom is lower energy when they are, and we like to be low energy. All right? Now, to get your electron configuration, I do not want 2, 5. I want the quantum configuration. Give me some more detail. So, in my 1s subshell, I have how many electrons? 1, 2. So you put a 2 exponent. Okay? In my 2s subshell, I have 2 electrons, so it's 2s2. In my 2p subshell, I have 3 electrons, so it's 2p3. This is the quantum configuration for nitrogen. You will always have those boxes except for the bonus. Okay? The bonus you should be able to do by just using your periodic table. Again, make sure you spread them out. Don't double them up until you have to. Make sure that your total number of arrows here matches the atomic number of nitrogen. So nitrogen is number 7. That means it has 7 electrons and 7 protons. So you should have 7 arrows, and I have 1, 2, 3, 4, 5, 6, 7. So that does match. Okay. Good luck.